Hi everyone! Today we're going to continue our discussion on chemical reactions. So last time we saw that chemical reactions can be divided up into two categories, non-redox and redox. Remember, in a redox reaction, we have reduction and oxidation, or in other terms, we have a transfer of electrons. In a non-redox reaction, we don't have a transfer of electrons. We also went over oxidation numbers, which is one way that we can use to determine whether we have a redox or a non-redox reaction. Now, within each of those categories are further subcategories. So under non-redox, we have combination reactions, double replacement reactions, and decomposition reactions. Under redox, we also have combination reactions, single replacement reactions, and we also have decomposition reactions. So there are some types of reactions that fall under both categories. It just depends on if we do have a transfer of electrons or if we don't have a transfer of electrons. But you'll notice that double replacement and single replacement reactions are only under one category. So let's start with decomposition reactions. In decomposition reactions, one substance is broken down into two or more simpler substances. Decomposition reactions may be either redox or non-redox reactions. So the general form for a decomposition reaction, we have one reactant, which we'll call A, and it's going to decompose and turn into multiple products, so B and C. Now, one example of a redox decomposition reaction is hydroiodic acid, HI, and it's decomposing into hydrogen gas and iodine gas. And then an example of a non-redox decomposition reaction is carbonic acid, H2CO3, and it's decomposing into carbon dioxide and water. So if we look at the redox decomposition reaction, the reason that it's a redox reaction is there is a transfer of electrons. So in our original reactant there, hydrogen has a +1 oxidation number because it is in a compound. And then iodine has a -1 oxidation number. And that's due to the fact that it is in group 7A. And all of the halogens in group 7A will have a -1 oxidation number. Now in the products, hydrogen is a pure gas, so that would have a value of 0. And iodine is also a pure gas, so it would have a value of 0. So we definitely have a difference in oxidation numbers from the reactants to the products, which tells us that we have a transfer of electrons. And then for the non-redox reaction, in the reactant, hydrogen has a +1 oxidation number because it is in a compound. Oxygen has a -2 oxidation number. And then we have to figure out what the oxidation number for carbon is. So we have 2 hydrogens, so I'll add another +1 here. And we have 3 oxygens, so I'll add -2 and -2. So if we add all of that up, we have +2 minus 6, so that's -4. And remember that for a neutral molecule, we should have an overall sum of 0. So in order to cancel out that -4 value, carbon must be +4. And then in the products, oxygen in carbon dioxide has a -2 value, and in water it also has a -2 value. Hydrogen always has a +1 value. And then in carbon dioxide we have 2 oxygens, so that's a total of -4. And in order to balance that, carbon must have a value of +4. So none of the oxidation numbers changed for the elements in this reaction, and that's why it is a non-redox reaction. But again, for a decomposition reaction, you have one reactant and multiple products. So a long time ago in chapter 1, we saw the reaction where hydrogen peroxide turned into water and oxygen. And this is a decomposition reaction. So we start out with H2O2, which is hydrogen peroxide, and that's going to decompose into water and oxygen. Now, another example of a decomposition reaction, you can decompose water and it will turn into hydrogen gas and oxygen gas. And I actually have a video here showing that process.
To separate the atoms that make up water, scientists need energy to break the bonds that hold the atoms together. To do this, they run an electric current through the water. Bubbles form in the tubes where the current makes contact with the water. These bubbles rise to the top of the tubes and fill them with clear gas. As the bubbles rise, they are captured to see what they are made of. One tube is filled up with twice as much gas as the other tube. Once the gas is collected, scientists test the bubbles' properties to determine what elements are present in the gases. One gas is determined to have a low density and will glow brightly in the presence of fire. Scientists can identify this gas as oxygen based on these properties. The other gas produced has twice as much volume as the first. This clear gas is determined to have an even lower density and reacts explosively when brought near a flame. These properties identify the gas as hydrogen. It is noted that no matter how many times the experiment is done, the results are always the same, and there is always twice as much hydrogen as there is oxygen.
Okay. So this experiment does also show us that we have twice as much hydrogen as we do oxygen, and that's shown in our balanced equation as well. The next reaction is a combination reaction. In combination reactions, 2 or more substances react to form a single substance. And combination reactions can be either redox or non-redox as well. So the general form of the equation for a combination reaction, which is also known as addition or synthesis, is A plus B. So again, we have 2 reactants, or you can have more as well. And then we're just producing one product. So an example of a redox combination reaction is sulfur reacting with oxygen to produce sulfur dioxide. And initially we have pure sulfur, so that would have an oxidation number of 0. And then we have pure oxygen, so we'd also have an oxidation number of 0. And then in the product, oxygen, remember, always has a value of -2, and there are 2 of them. So that's a total of -4. So sulfur, to balance that out, must have a value of +4. So we definitely have a change in oxidation number for sulfur and oxygen over the course of the reaction. So that tells us that this is a redox reaction. And then an example of a non-redox combination reaction, we have N2O5 reacting with water to produce something called nitric acid, HNO3. And let's go through and assign oxidation numbers. So for oxygen, remember that's always -2, and there's 5 oxygens, so we'll multiply that by 5. So that gives us an overall value of -10 for all of those oxygens. And then nitrogen, or the 2 nitrogens there, have to balance that. So those 2 nitrogens have to add up to +10. So if we divide that by 2, each nitrogen has a value of +5. And then in water, we saw before that hydrogen has a +1 oxidation state or oxidation number, and oxygen has a -2 oxidation number. And then in the product, HNO3, hydrogen still has a +1 oxidation number. Oxygen still has a -2 oxidation number, and there's 3 of them. So if we add that up, we have +1 minus 6, so that's -5. So to balance that out, nitrogen must have a +5 oxidation number. All right, so nothing changed in that reaction. Everything still has the same oxidation number from beginning to end. So that would be a non-redox combination reaction. We did not see a transfer of electrons. All right, now also at the very beginning of our class, we saw that hydrogen reacts with fluorine to produce hydrofluoric acid. And this was a combination reaction. We had 2 reactants and only 1 product. So we were just combining those reactants to end up with our final product. And another example of this reaction, if we combine solid aluminum with liquid bromine, we end up with aluminum bromide. Let's watch that reaction. That's really bad.
To start, bromine is added to a test tube. This is bromine that was made in a previous video and it was stored in my homemade ampule.
Here, let me see if I can get it to, there we go.
Ampules. I show here that it can be easily opened by breaking it open with a pair of pliers. Then, aluminum foil is added to the test tube. Due to the protective oxide layer on the outside of the aluminum, it takes a little while to react. The aluminum reacts violently with the bromine to form aluminum bromide. When slowed down to about 1/4 the speed, you can actually see a molten red-hot ball of aluminum bouncing up and down the test tube. The white pieces that you see flying out of the test tube is actually liquid aluminum. When the reaction is done, a little bit of water is added to the test tube and you can see that it reacts pretty violently. This happens not only because the test tube is still hot, but it contains a lot of aluminum bromide which reacts exothermically with the water. Eventually enough water can be added to fully neutralize all the aluminum bromide and cool down the test tube. When the test tube had been cleaned out, what was found at the bottom was a solid ball of aluminum metal. The reaction actually got hot enough to liquefy and melt the aluminum. I decided to do a second.
All right, so if you want to watch the rest of that video, feel free to click on the link on your PowerPoint slides. But we also saw this reaction on the Theodore Gray app a few chapters ago in chapter 3. So that's always a fun reaction to watch. All right, next are single replacement reactions. So single replacement reactions are always redox reactions because they occur when one element reacts with a compound. So the element is going to displace one of the elements from the compound, and it becomes part of a new compound. So if we write the general form for this reaction, also known as a substitution reaction, we have an element A and a compound BX. And A is going to replace B. So at the end of the reaction, we end up with B as a pure element and the compound AX. So B and A switched places. So one example of a single replacement reaction is pure zinc reacting with copper sulfate to produce copper and zinc sulfate. And remember, these are always redox reactions. So if we just focus on zinc and copper, zinc starts out as a pure element, so it has an oxidation number of 0. And then copper has a +2 oxidation number here because sulfate has a -2 oxidation number or charge. And then in the products, copper is a pure element, so it has a 0 oxidation number. And then zinc has replaced copper. So now zinc has a +2 oxidation number. And then this sulfate polyatomic ion still has an oxidation number of -2, which is equal to its charge. So zinc and copper definitely transferred electrons in this case. Zinc went from 0 to +2, and copper went from +2 to 0. So that is definitely a redox reaction. Now another example is copper, which can react with something called silver nitrate to produce silver and copper nitrate. So you can actually end up with pure silver at the end of this reaction. And in the video that we're about to watch, silver nitrate, which is an aqueous solution, is added to a copper penny. And that penny eventually gives up its copper and turns it into silver. So from your lab, remember that pennies prior to 1982 were essentially pure copper. So this penny is from 1977. And then they're adding silver nitrate. And now you can see that pure silver is forming, and the copper is turning into copper nitrate. So that video does go on longer, so you can watch the full reaction if you want to. There's the link below. And now for double replacement reactions. So double replacement reactions are never redox reactions. These reactions often take place between substances dissolved in water, so aqueous solutions. And in typical reactions, two dissolved compounds will react and exchange partners. and then they form two new compounds. So down below we have a general reaction. So we have two compounds, AX and BY, and they're going to flip partners. So another way of looking at this is A and B are going to switch places. So we're just going to flip A and B. So then we'll end up with BX and AY as our products. So an example of a double replacement reaction is barium nitrate reacting with sodium sulfide to produce barium sulfide and sodium nitrate. And again, everything will maintain its oxidation numbers throughout, so there are no electrons being transferred during this process. And here we have another example of a double replacement reaction. So when sodium chloride, or table salt in its aqueous form, reacts with silver nitrate, silver and sodium are going to flip places. So we end up with sodium nitrate and silver chloride. Now, silver chloride actually is a solid in solution. And that's partly due to the fact that silver and chlorine have such a strong bond with each other that they end up precipitating out of solution. So we would actually call this product a precipitate. And I have a short video showing this process. Here, let me see if I can get this to, there we go. All right, so we have two clear solutions, but when they're mixed together, a white precipitate, silver chloride, forms. So we say that silver chloride is precipitating out of solution. All right, and we'll learn more about precipitates later on. We'll learn some rules that will tell us, what actually can form a solid in solution. Because you'll notice that the other product in this reaction, sodium nitrate, is still aqueous. So that means that sodium and nitrate are kind of just floating around in solution. They're not forming a solid, but we can still write them as if they're a product. So let's do a couple of practice problems where we try to classify different reactions. So we're going to classify each of the following equations as redox or non-redox reactions. And then we're going to further classify them as combination, decomposition, single replacement, or double replacement reactions. So let's start with the reaction below. So we have sodium hydroxide and hydrochloric acid, and then they're reacting to form sodium chloride and water. So let's make a little table of oxidation numbers. So we'll do reactants versus products. So let's start with sodium. And in the reactant, sodium is a +1 ion because it's combined with hydroxide, which is a polyatomic ion. So sodium, because it's a group 1A metal, would have a +1 oxidation number. And then in the products, sodium is still an ion. It's bound to the chloride ion. So it will still have a +1 oxidation number. And then oxygen, our next element, again, always has a -2 oxidation number if it is in a compound. So in the reactants, it is in a compound, so we would assign it a value of -2. And then in the products, it's also in a compound, water. So it would also have the value -2. And then our next element is hydrogen. And hydrogen is in both reactants, but both reactants are molecules. So hydrogen will have a +1 oxidation number within both of those molecules. And same for the products. Hydrogen is present in water, so it would still have a +1 oxidation number. And then chlorine is present in a molecule in the reactants, and it's in group 7A, so it will have a -1 oxidation number. And then in the products, it's in an ionic compound, and its charge is -1, so its oxidation number will be -1. So none of the elements exchanged electrons. All of their oxidation numbers stayed the same. So this means that we have a non-redox reaction. And let's try to classify this as combination, decomposition, single replacement, or double replacement. So remember that decomposition reactions only have one reactant, so we can already rule that one out because we have two reactants. And then remember that in a combination reaction, we only have one product, but here we have two products, so we can rule that one out. So now we have to decide if this is a single replacement reaction or a double replacement reaction. Now, remember in a single replacement reaction, we have one element and one compound in the reactants. And that's not the case here, so we can rule out single replacement. So that means we have a double replacement reaction. And you can kind of see how that's working here. So sodium and hydrogen are switching places. So we end up with NaCl, sodium chloride, and H2O, water. All right, now let's classify this reaction as redox or non-redox, and then we'll further classify it as one of our 4 types of reactions. So again, let's make our little table. And if you ever want to try this on your own, feel free to pause the video first, and then you can unpause it and see if you got the same answer. So let's start with magnesium. So in the reactants, magnesium is by itself, which means it's a pure element. So we would assign it an oxidation number of 0. But then in the products, magnesium is in an ionic compound. So remember, magnesium is a metal, oxygen is a nonmetal, so this is an ionic compound. And what is the charge on magnesium? +2. So that means that the oxidation number of magnesium is +2. And then oxygen is our next element. And in the reactants, oxygen is just by itself, so it's a pure gas. So it would have an oxidation value of 0. But then in the products, oxygen is in a compound, so it would have a -2 value. All right, so we definitely see a change in oxidation numbers. So magnesium is losing electrons because remember it's ending up with a positive oxidation number or a positive charge. So that would be a loss of electrons. Whereas oxygen goes from 0 to -2, so it's gaining electrons. So it has a more negative value now. Now, remember our acronym, oil rig, or Leo the lion says grr. So if something is losing electrons, is that oxidation or reduction? Right, it's oxidation. And if something is gaining electrons, is that oxidation or reduction? Reduction. Okay. And now that we know we have oxidation and reduction, we know that we have a redox reaction. Okay, so now we need to further classify this reaction as combination, decomposition, single replacement, or double replacement. So right off the bat, we can probably eliminate decomposition because we have two reactants, and a decomposition reaction would only have one reactant. All right, and then let's see, let's go to combination next. So in a combination reaction, we only have one product. And that's exactly what we have here. So this would be a combination reaction. Now this reaction is not a single replacement reaction because remember in a single replacement reaction we have one element and one compound in the reactants. But here we have two pure elements. And then double replacement reactions have two compounds in the reactants, and we have two pure elements. So the only possibility here is combination. All right, and here's the solution slide. Let's do a couple more problems just so we can really see how this works. Okay, so for this reaction, again, let's divide up reactants versus products. And we'll try to determine if this is a redox or non-redox reaction. So starting with sodium, it is in a compound and it is a group 1A metal. So it would have a +1 oxidation state. And then in the products, it's also in a compound, and that would mean it also has a +1 oxidation state. All right, and then let's go to oxygen because we don't have a rule that gives us a value for carbon. We have to determine the value of carbon from the other elements in the compound. So let's jump to oxygen next. So when oxygen is in a compound, it always has a value of -2. And in the products, oxygen is part of two compounds. So in both of those compounds, oxygen has a value of -2. And now we can figure out the value for carbon. So in the reactants, we have two sodium ions, each with a +1 oxidation number. And then we have three oxygens, each with a -2 value. So if we add that up together, we have +2 minus 6. So that would be -4. So to balance that out, carbon must be +4. Because remember, we want everything to add up to 0. Now in our products with carbon, we have two oxygens, both with a value of -2. So that's a total of -4. So to balance that out, carbon has to be +4. All right, so it looks like none of our oxidation numbers changed, which means we have a non-redox reaction. So there was not a transfer of electrons. Now let's figure out if this is a combination, decomposition, single replacement or double replacement reaction. All right, now remember, combination reactions involve 2 or more reactants and only one product, which does not describe this reaction, so we can eliminate that. Decomposition reactions have only one reactant and multiple products, and that does describe this reaction. So we can stop there. Now, this wouldn't be single replacement or double replacement because both of those reactions have 2 reactants, which is not the case here. All right, so this is a non-redox decomposition reaction. And one last equation. So let's classify this as redox or non-redox. So we'll do the same thing that we have been doing. We'll divide up reactants versus products. And let's start with magnesium. So magnesium, it's by itself in the reactants. So that must mean it's a pure element. So it has an oxidation number of 0. But then in the products, magnesium is in an ionic compound. So magnesium is a metal, chlorine is a nonmetal, so that's an ionic compound. And what is the charge on a group 2A metal? +2. So magnesium has an oxidation number of +2 in the products. Now let's go to hydrogen. So in the reactants, hydrogen is in a molecule, so it will always have a value of +1 in a molecule. And then in the products, hydrogen is by itself. So that must mean it's a pure element. Now remember, hydrogen does like to pair up with another copy of itself, even in its pure elemental form. So it is written as H2, but it is a pure element. So we would give it a value of 0. And then our last element is chlorine. So chlorine is a group 7A metal, or nonmetal, excuse me. And it's a halogen. And what is the charge typically on chlorine? -1. So group 7A nonmetals will have a value of -1 in a molecule. And then in the product, chlorine is also -1. All right, so chlorine's oxidation number did not change, but magnesium's oxidation number did change, and hydrogen's oxidation number changed. So magnesium is going from 0 to +2, so it's becoming less negative, which means that it lost electrons. And then hydrogen is going from +1 to 0, so it's becoming more negative. So it's gaining electrons. And remember from our acronym, oil rig, loss of electrons means oxidation. Gain of electrons means reduction. So we definitely have a redox reaction. Okay, so now let's figure out if this is a combination, a decomposition, a single replacement, or a double replacement reaction. Now let's start with combination. We know that combination reactions have just one product, and that's not the case here, so we can eliminate that. Decomposition reactions only have one reactant, and that's not the case here, so we can eliminate that. And then a single replacement reaction has a pure element and a compound in its reactants. And that is the case here. So this would be a single replacement reaction. And then remember that a double replacement reaction would have two compounds or two molecules in the reactants, and that's not the case here. We have a pure element and a molecule. Okay. And then here is the solution slide. So feel free to go back and watch those YouTube videos further if you would like. And I will see you in the next video.